Welcome to qnawire.
Hi, we're going to have the titration of 70 milliliters of a 0.5060 molar dimethylamine solution with 0.1817 molar HCl at the same temperature, and we're given the value for the pKb for dimethylamine. So the first thing that we need to identify is the amount of mole that we're going to have of dimethylamine in solution, that is going to be equal to the volume in liter times the concentration in molarity. The volume in liters is going to be 70 times 10 to the minus 3 liters, converting milliliters into liters directly, times the concentration, 50-60 molar. So the amount of mole that we're going to have initially is going to be equal to 0.03542 mole of the amine that we're going to have. In this case, the reaction of the titration is going to be a 1-to-1 reaction, so that means that we're going to require the same amount of mole of HCl, or to be more proper, of H2O plus in order to titrate this solution. So this implies that the volume required of HCl would be equal to the amount of mole of HCl required divided by the concentration in molarity of HCl. This is going to be 0.03542 mole divided by the concentration of 0.1817 molar. This is going to give us 0.1949 37 liters. In this case, we need to round up to three significant figures, since this is going to be the quantity with the least amount in our calculation. So the volume required of HCl would be equal to 0.195 liters. But in this case, let's use 1949s just to keep up with the number that we're going to get, which is the same as 194.9 milliliters. After the addition of 70 milliliters, the volume at the equivalence point would be equal to the sum of the initial volume, 70, plus the value that we have here. So we're going to have 264.9 milliliters, or 0.22649 liters. This is going to be our volume at equivalence. So with this information, we can now proceed with our calculations. The reaction that we're going to be considering is going to be that of dimethylamine plus HCl, that is going to produce the dimethyl ammonium ion, NH2 plus Cl minus into the solution. In this case, at the equivalence point, given the amount of mole that we had initially, we have added the same quantities of HCl and of dimethylamine. So that means that at equilibrium, we're going to assume first that we're going to have a complete reaction, and we're going to generate the initial amount of dimethyl ammonium. Dimethyl ammonium is going to have a pKa associated to the pKb. Remember that pH is going to be equal to, pKw is going to be equal to pKa plus pKb, and at the same time, this is going to be equal to 14. Thus, the value for pKa would be 14 minus pKb, which in this problem is given to be 3.27. So 14 minus 3.27 is going to give us the pKa of 10.73, associated to the following reaction. The reaction that we're going to consider is going to be that of the methyl ammonium with water in order to produce H2O plus dimethylamine. In this case, we can calculate the initial concentration using the amount of mole that we have, the initial amount of mole, and the total volume on our concentration. So my initial concentration would be, I'm going to label the initial concentration as C0, over here, C0 would be equal to the amount of mole divided by 0.2649 liters. And the amount was 0.03542 mole, which is an initial concentration of 0.1337 molar. So this is going to be my initial concentration. Now my ice table is going to be in terms of molarity. And what we're going to get is that initially we're going to have C0. Water, it doesn't matter. It doesn't enter into the equilibrium calculations. Let's say that we have a change of minus x, and plus x. At the equilibrium, we would get C0 minus x, and this is going to be equivalent to the Ka equation. Thus, over here, the value for Ka, which is equal to 10 to the minus 10.73, is a very small value, would be equal to the concentration of H3O plus times the concentration of CH3-2NH, the dimethylamine, divided by the concentration of the weak acid, which is the methyl ammonium ion. Replacing the values that we got at the equilibrium, we're going to get x squared divided by C0 minus x. In this case, Ka is very small, so we're going to employ the small x approximation. Thus, C0 minus x would be approximately equal to C0 directly. That implies that the value for x, well, first of all, x squared over C0 would be equal to Ka, leading us to x being equal to the square root of Ka times C0. Replacing the values that we got, 10 to the minus 10.73 times my initial concentration of 0.1337 gives us a value of x equal to 1.5778, 5 times 10 to the minus 6, and this is going to be equal to the concentration of H3O plus that we're going to have in equilibrium. So the pH is equal to minus the logarithm of this concentration. In this case would be minus logarithm of x, which gives us a pH equal to 5.80, 802. And in this case, we're asked to round your answer to two decimal places, so the pH would be equal to 5.80. And with that, it would be all. Thank you very much, and have a good one.